Hello, let's work through the problems out of section 5.8. All right, getting right into it. So we are given an exponential function right here that models the population, P, of an insect population after T days. Okay, so if I want to determine the number of insects at T equals 0 days, I really just have to plug in T equals 0. So P of 0 equals 600 e to the 0.05 times 0. Now here I end up with e to the 0, and e to the 0 is 1. Anything to the 0 is 1, except for 0 to the 0, which is undefined. So here we end up with 600. So P of 0 is 600. The population begins at 600 insects. Note the similarity to the continuously compounded interest formulas, where this number here would be your principal investment, or the amount of money you start with. So how many insects do we start with? 600. Okay, so for part B, what is the growth rate of the insect population? Well, again, comparing this to our financial formulas from previous sections, this really looks like continuously compounded interest, where this is our final amount of money, this is our principal investment, and the growth rate is this R right here at 5%. C. What's the population after 10 days? All we have to do is plug in T equals 10. Okay. And again, I'm just going to pull out a calculator on the side just to compute this quickly. This is already an exact answer, but if my lab or your particular professor wants a 2-decimal approximation, then you're going to have to do that. I get a result of 989.23. But since we are talking about insects, I'm actually not going to round this to 2 decimal points. I'm just going to round it to the nearest whole number, and I'm going to say this is about 989. Insects don't pop out, half-formed, usually. So when will the insect population reach 780? Well, then I know I want the population to be 780, but the unknown is T. So if I divide by 600, okay, so we have 78 over 60 is equal to e to the 0.05t. I can convert this into a natural logarithm to get 0.05t is equal to the natural log. Let's see, 78 over 60 can be simplified further. This is going to be 39 over 30, or 13 over 10. So 0.05t is the natural log of 13 over 10, and then I just have to divide by 0.05. And quickly computing this, .25, so 5¼ days. Okay, since this is not measuring insects but days, I'm perfectly fine rounding to 2 decimal points here. And finally, freeing up some space on the left, when will the insect population double? Well, we specified in part A that we started with 600 insects, so doubling would be 1,200 insects. So I just set 1,200 is equal to 600 e to the 0.05t. Dividing by 600 gives me 2 is equal to e to the 0.05t. In other words, 0.05t is the natural log of 2, so t is the natural log of 2 over 0.05. And again, this is already exactly correct. If you want a 2 decimals estimation, we've got 13.86 days. So in about 14 days, we'll have doubled our insect population. Okay, moving on. So we have a colony of mosquitoes obeying the law of uninhibited growth. That's just the exponentially growing population model from the previous problem, and it is the same formula as continuously compounded financial interest. So if n is the population of the colony, t is the time as in days, express n as a function of t, where n sub 0 is the original amount, and k is a constant that represents the growth rate. So this is really just a matter of writing down the same formula, but with slightly different letters. So n of t is the principal investment amount, or the starting population, which they've called n sub 0, times e to the growth rate, which we are told should be represented with k, times t. Okay, part B, the population obeys the law of uninhibited growth, so we're going to use that formula right there. If there are 1,000 mosquitoes initially, so that's our starting amount, and there are 1,900 after 1 day, so n of 1 is 1900. What is the size of the colony after 2 days? So find the value of n of 2. Okay. So if n of 1 is equal to 1900, after 1 day we have 1900 mosquitoes. If we use the law of uninhibited growth starred up here, we can also say that n of 1 is n sub 0 e to the kt. But we know that t is equal to 1 and n sub 0 is equal to 1000. Okay, so we also know n of 1 is 1900. Altogether, we get 1900 n of 1 equals 1000 n sub 0 times e to the k times t, and t is just 1. So we end up with 1900 equals 1000 e to the k, and this is going to allow us to solve for the value of k. Dividing both sides by 1000, we have 1.9 is equal to e to the k, or k is equal to the natural log of 1.9. I'm actually not going to round this off because I don't want to introduce compounding rounding errors, okay? Because we're not actually done with the problem yet. What we were actually asked to find out is, what is the size of the colony after 2 days? So, in other words, we need to evaluate n of 2. Well, n of 2 is 1000 e to the kt, but we've just determined the value of k, and we determined it exactly. So we have 1000 e to the natural log of 1.9 times t. And t in this case is 2. And now, since I haven't introduced rounding errors when computing natural log of 1.9, I'm not going to get, errors on top of errors here. So we can get an answer 1000 times e to the 2 times the natural log of 1.9, and we have 3610. Okay, that seems a little bit high. I'm just double checking. No, that looks correct. Yes, sorry. This actually makes quite a lot of sense in terms of the size. So in 1 day, we went from 1000 to 1900, which was almost doubling. So 1 more day should almost double again. So double 1900 would have been 3800, but we didn't quite double from day 0 to 1. It was 1000 to 1900, so we shouldn't quite double to go from day 1 to day 2. So we don't quite go up to 3800, but fairly close. Okay, part C, I'm actually going to erase everything off the page because I need to do part C. What I do want to make note of, however, is that k, we've already determined the value of. It's the natural log of 1.9. Okay, so I'm going to rewrite that because we've already found that out. K is 1.9, sorry, natural log of 1.9. So how long until there are 90,000 mosquitoes? We want to end up with 90,000. We started with 1,000. And now we have e to the k, which we've already determined is log of 1.9, times t. So divide both sides by 1,000 to get 90 is equal to e to the natural log of 1.9 times t. Converting this to a natural log, we get the natural log of 90 is equal to the natural log of 1.9 times t. Divide by natural log of 1.9. And again, since I haven't introduced a rounding error when computing the value of k, I'm not going to get a worse rounding error here. Natural log of 90 divided by natural log of 1.9 is 7.01. So it's only going to take about 7 days to have gone from 1,000 mosquitoes to 90,000. I guess they breed pretty quickly. Okay, a pizza pan is removed at 8 p.m. from an oven whose temperature is fixed at 425. As soon as we see that we're dealing with temperatures and moving stuff around, we're dealing with Newton's law of cooling. Okay, so Newton's law of cooling is frequently a source of some confusion. You just want to double check to make sure you've got the formula correct. So I frequently end up looking it up myself because I want to make sure that I haven't made any errors. Okay, there we have it. So depending on your source, the letters might be different. So what I've just looked up gives me the following. T of t equals T sub s plus T sub 0 minus T sub s e to the minus kt as a formula for Newton's law of cooling, okay? Where T sub 0 is the initial temperature of your object, T sub s is the temperature of the surrounding environment, okay? K is some constant representing how fast temperature changes in a given object. T is time. And capital T on the left is the temperature of your object at time t. So what we have to do is match up our given information here. So the oven temperature is fixed at 425. The room is fixed at 74. So which one of these represents the temperature of our surrounding? Well, since the pizza pan was removed from the oven and is then left outside the oven, for the purposes of this pizza pan cooling after 8 p.m., after being removed from the oven, the surrounding temperature is 74. However, we can assume the pizza pan begins at a temperature of 425 because it was brought out of that oven. Okay. After 5 minutes, the pizza pan is 300 degrees. So after 5 minutes, capital T of 5, the temperature of the pan, is 300. So that's going to allow us to find the value of K. Referring to the formula for Newton's law of cooling, I'll know this left-hand side. T of 5 will be 300. I'll know T, it will be 5. And we know the surrounding temperature, 74 degrees, and the starting temperature, 425. So the only unknown left will be K, and we'll be able to find it. So let's go ahead and do that. Okay, so if T of 5 is 300, we get 300, that's T of 5 on the left, is equal to the surrounding environment, 74, plus the starting temperature, 425, minus the surrounding temperature, 74, times e to the minus k, and I don't know that, but T was 5. Okay, if T of 5 is 300, we've gone ahead and plugged in T equals 5. Okay, I'm going to subtract 74 from both sides to get 226 is equal to 425 minus 74 is 351 times e to the minus 5 times k. Now I can divide by 351. So we get 226 over 351 is equal to e to the minus 5k. Convert this to a natural logarithm. Minus 5k is equal to the natural log of 226 over 351. Now divide by negative 5. And I'm going to write this up at the very top of the page because we are going to use it a couple of times. So k is equal to negative 1/5 times the natural log of 226 over 351. And again, I'm not going to compute this to 2 decimal points because I don't want to introduce further rounding errors later. Observe, part A didn't actually ask us to find what's the value of K. None of it does. All we've done is use the information after 5 minutes, the pizza pan is at 300 degrees, to determine the value of K. So now in this Newton's law of cooling, the surrounding temperature and the starting temperature are known, and now we know the value of K, so we can quite directly plug in T and get out temperature, or vice versa. Okay, so now we are actually equipped to go on and actually start part A of the problem. All we've done so far is use the given information to determine the value of K. In these sorts of scenarios, K represents something intrinsic about the material of your object, related to how fast energy moves through it. So our pizza pan, for example, might change temperature a lot faster than some sort of object that's got some insulation on it. It might change slower than maybe a big block of like solid steel or something, which can radiate heat away quite quickly. Anyway, part A. At what time is the temperature of the pan 130? So I know I don't know time. Oh, I shouldn't have erased Newton's law of cooling. Sorry, I'll put it back up here. T of T is the surrounding temperature plus the difference between the starting and surrounding temperature times e to the minus kt. There we have it. Put a box around it so I don't accidentally erase it. So now we know the left. We know the temperature at a given time. I want it to be 130. What I don't know is the time t. Everything else I still know. So my surrounding temperature is 74. I started at 425 minus the surrounding temperature of 74, e to the minus kt. We know the value of k. Remember, we determined it up here. I'm just not writing it here because it will take a lot of space to write. I'm not going to replace k with this value until the very end, but I do remember that I actually know this value. Okay, but by not writing this mess over and over and over again, I'm limiting the number of times I could make a mistake just from writing a number down wrong. Anyway, I subtract 74. That cancels that. 130 minus 74 is 56. So I want 56 to be equal to 351 times e to the minus kt, divide by 351. So 56 over 351 is e to the minus kt. Convert this to a natural log. E to the minus kt is equal to the natural log of 56 over 351. Now I can divide by negative k. So t is equal to the natural log of 56 over 351 over negative k. And now I'm going to go ahead and plug in my value of k. Note, by the way, up at the upper part of the page, k has this minus sign built into it. So negative k will cancel that minus sign out. So I end up with the natural log of 56 over 351 over 1/5 the natural log of 226 over 351. Dividing 1/5 down in the denominator, I'm just going to bring up to the numerator as a 5 times the natural log of 56 over 351 over the natural log of 226 over 351. And now I'll go ahead and pull out a calculator to estimate this. 5 times log of 56 over 351 divided by natural log of 226 over 351. 20.85. So just shy of 21 minutes later, the pizza pan will be 130 degrees. Still pretty warm to the touch, but not instant burn territory. Okay, so for part B, it's very similar. Okay. Oh, at what time? Sorry, this was 20.85 minutes past. So since we began by pulling the pizza pan out at 8 p.m., the correct answer would be 8:20 or maybe 8:21 p.m., depending on exactly how you're supposed to round minutes. Okay, T represents the time elapsed. And since 8 p.m. represents 0 time elapsed, 21 minutes later should be 8:21 p.m. Okay, part A, done. Part B. Determine the time that needs to elapse before the pan is 230. Very similar to what we've just done, but I want the temperature of the pan to be 230. So we set that up as 230 equals 74 plus 425 minus 74 e to the minus kt. Once again, I'm not going to put in the value for k until the very end because I don't want to accidentally write it down wrong. Okay, so 230 minus 74 is 156. Notice this is pretty much the same work we've done. Okay, so I end up with 156 over 351 is equal to e to the minus kt. I convert it to a natural log to get e to the minus, just negative kt is equal to the natural log of 156 over 351, divide by negative k. So t is equal to the natural log of 156 over 351 over negative k. That's going to give me the natural log of 156 over 351 over 1/5 natural log 226 over 351. And I'm just going to move that 5 into the numerator as I did before. And going ahead and estimating this, $9.21. So after 9.21 minutes, the temperature of the pan will be 230 degrees. Now part C, what do you notice about the temperature as time passes, is pretty vaguely worded. but I'm going to just erase some of this so that I can clear up some space and then look at the equation for Newton's law of cooling. And what we're going to do is we're going to ask what happens to this as time goes on and on, as T gets bigger and bigger. So on the right-hand side of Newton's law of cooling there, we've got T sub S. That can't change. That's the temperature of the surrounding environment, and part of the assumptions of Newton's law of cooling is that this is not changing. Okay, so not changing. Also, our initial temperature is not changing. The temperature that we are at any given time is certainly changing, but T sub 0 is the temperature we started at. That's just some value. The only thing that's changing is this. So what happens to e to the minus kt? So how does e to the minus kt change as t increases? Well, notice this is an exponential curve. Okay, so it either looks like this or it looks like this. Which one is it? It's the one on the right because I have a negative exponent here. Newton's law of cooling, the version I found here, it's quite explicit that k is supposed to be positive, and so when you put that minus sign in front of it, you get a negative exponent here. Which means this has a horizontal asymptote of y equals 0 as t gets bigger and bigger. So specifically, as t gets larger and larger and larger, this term goes to 0, which means this term here is now being multiplied by 0. So as t gets bigger, this function has a horizontal asymptote of T sub s, whatever that is. Now T sub s represented the temperature of the surrounding environment. So Newton's law of cooling is saying something that is intuitively fairly obvious. If you take this pizza pan out of the oven and leave it in the room and just wait forever, the temperature of the pizza pan will gradually approach the temperature of the room, 74 degrees. It's not going to get colder than that, and it's not going to stay at 90 degrees, for example, forever. Eventually it's going to cool down and just keep getting closer and closer and closer to 74 degrees. So that's what part C is getting at. Okay, now we have something called a logistic model. It looks a bit more complicated, but it's still just fundamentally an exponential function of one variety or another. Okay, it represents the percentage of households that do not own a personal computer in where T is measuring years since 1986. Okay, so for example, if T is equal to 3, that represents the year 1989. Okay, so evaluate and interpret P of 0. Well, first we just have to evaluate it, so I'm just going to plug it in. 94.3954, yuck. 1 plus 0.0379 e to the 0.1702 times 0. Well, here I get an exponent of 0, and e to the 0 is equal to 1. So this is just going to be 94.3954 over 1 plus 0.0379. I don't need a second decimal point in there. That was silly. Okay. Well, since they're clearly wanting us to work with lots of decimal points, I will do that as well and compute this. 3954 over 1.0379, 90.95. Okay, so we've evaluated it, but let's actually interpret it. So this represents the percentage of households that do not own a personal computer in the years since 1986. So if T is 0, that means no years have elapsed since 1986. So this is the percentage of homes with no computer in the year 1986. Okay. That's part A. Part B is using a graphing utility to graph this. We'll actually come back and I'll copy something at the end. What percentage of households did not own a personal computer in 1997? So this is 11 years after 1986. Just by doing 1997 minus 1986, you get 11. In other words, I'm going to let t equal 11. So P of 11 is equal to 94.3954 over 1 plus 0.0379 e to the 0.1702 times 11. So bringing out the calculator, 0.0379 times e to the 0.1702 times 11, close parenthesis, 75.73. Okay, so what percentage of households did not own a personal computer in 1997? About 75% of homes didn't have a computer. Part D, in what year will percentage of households that do not own a personal computer reach 20%? Okay, so much like previous problems, now what we're going to do is we're going to know the value on the left and we have to solve for t. Okay, so we know we want 20% to be the percentage that don't have a computer, and I set that to be 94.3954 over 1 plus 0.0379 times e to the 0.1702 times t, and we need to now solve this for t. So I'm going to multiply both sides by this denominator, aka cross multiply. Okay, so we get 20 times this whole mess equals 94.3954. I'm going to divide both sides by 20. So now what we have is, again, I just need a bit more space because this is, the fact that they've given us 4 decimal points of accuracy for all of our numbers just means this takes a lot of time to write. Okay, so on the left we have 1 plus 0.0379 times e to the 0.1702 is equal to 94.3954 over 20. So now I'm going to subtract 1. Okay. Notice that 1 can be replaced with 20 over 20. So on the right, I can just call this 74.3954 over 20. And on the left, I have 0.0379 times e to the 0.1702. Divide both sides by 0.0379. Cancels that. Okay, so I'm going to clearly write over here. On the left, we have e. Oh, I forgot my t. I apologize. It was e to the 1.1702 t. That's important. 0.1702 t. On the right, we have 74.3954 over 20 times 0.0379. Now I'm going to convert this to a natural logarithm. Okay, so we get 0.1702 t is equal to the natural log of all of this mess, 74.3954 over 20 times 0.0379. Finally, I can just divide by 0.1702. And I'm moving back over to the left here. Okay, but we are now basically done. If I divide by 0.1702, we get t is equal to the natural log of 74.3954 over 20 times 0.0379 all over 0.1702. Now it would be nice to compute this. Bear with me, it's going to take some time to enter this into a calculator. Natural log 74.3954 over 20 times 0.0379, close that denominator, close that natural log, divided by 0.1702. I'm double checking. There's a lot of decimal points to enter in here. I just want to make sure they're all entered correctly. 74.3954 over 20 times 0.0379 divided by 0.1702, and then I get 26.95. I'm just going to round this up to 27 for the sake of having a nice whole number because we are counting years. But Part D didn't say how many years need to elapse. Part D asks in what year. So this measures 27 years elapsing since the year 1986. So 27 years after 1986 means the year is 1986 plus 27, which is 2013. So in the year 2013, only 20% of homes did not have a computer according to this model. Now, I did say we were going to come back and graph this function. So 94.3954. If you don't know, by the way, you can enter equations of the form y equals something as a variable of x into most search engines, and it will produce a graph for you. So instead of using t as my variable, I'm just going to call it x because that's what works automatically. 0.3954 divided by 1 plus 0.0379 times e to the 0.1702 x. And I'm using x just because in the search engine that's what will be produced. Okay, so the function looks something like this. Okay. So we've already found that at t equals 0, the result was 90 point something. Okay, so the graph starts here. As time progresses, the percentage of homes without a computer falls and starts falling quite quickly. But the percentage of homes without a computer can't go below 0. That doesn't make any sense, and this sort of function actually captures that behavior. It's falling quite quickly, but then it starts slowing down. It has a horizontal asymptote of y equals 0. This is referred to as the logistic model, and it does the following. It tends to model things exhibiting exponential either growth or decay, but with some sort of boundary that it can't cross. This is exponentially decaying, but I can't go below 0. There's some sort of other force that says as the number of homes without a computer gets close to 0, whatever is making people buy computers isn't affecting those people very much. Probably they just can't afford it. Okay, so people are buying computers, but there's a floor that it's not going to pass through, and the function slows down a lot as it gets close to that. Logistic models can also be used to represent population growth, where for some reason the population is never going to pass this quantity. Like the field can only support a maximum of so many mice. So you introduce a few mice and they start breeding very, very, very quickly, but as they get closer to what's called the carrying capacity, they just can't breed as much. There's just not enough space for them. It slows down and it has a horizontal asymptote. So a logistic model captures things that behave exponentially until they reach some sort of limiting value.